Tonight, we drift into one of the most incredible ideas ever imagined, the invisible fabric that shapes everything we see and everything we are, space-time. The stage upon which every star burns, every planet turns, and every heartbeat unfolds. From the bending of light around galaxies to the slowing down of clocks, space-time weaves the universe together in ways both elegant and strange. It curves near matter, stretches where the cosmos expands, and hums with ripples from colliding black holes. Even the air around you belongs to its vast design. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. For now, just breathe, let your eyes grow heavy, and let the cosmos cradle your thoughts. Let's begin. Space-time is the fabric that holds the universe together. It is not just a background stage where events unfold, but the very structure that defines how everything in the universe exists and moves. Every planet, every star, and every atom sits within it, shaping it and being shaped by it in return. It combines 3 dimensions of space with one of time into a single 4-dimensional continuum. When mass or energy is present, this continuum curves, creating what we experience as gravity. When it is empty, it remains smooth and flat. Yet, even that apparent emptiness has properties capable of stretching, compressing, and transmitting waves. Without this unifying fabric, distances and durations would lose meaning, and no consistent laws of motion could exist. It is the invisible stage and the active participant, the quiet geometry that keeps the cosmos coherent from the smallest particle to the vast web of galaxies. Time and space are not separate things. For centuries, space and time were seen as distinct, one describing where things are, the other describing when things happen. Einstein's work showed that they are deeply connected, inseparable parts of a single structure. The movement of an object through space affects how it experiences time, and the passage of time can influence how distances are measured. This means that a clock carried by a moving observer will not tick at the same rate as one at rest, and rulers in motion will appear shortened to those watching. The 2 quantities blend into one system that adjusts itself to keep the laws of physics identical for everyone. Every event in the universe can only be fully described by including both its position and its moment, forming a 4-dimensional coordinate. This realization reshaped physics forever, revealing that reality is far more interconnected than our everyday experience suggests.
Einstein's insight changed our understanding of reality forever. Einstein's theory of relativity redefined what it means to measure motion, distance, and time. Before his work, scientists assumed these values were absolute and universal. Einstein recognized that measurements depend on the observer's state of motion, and that all observers must agree on the speed of light. This simple principle forced everything else to adjust. Time slows for moving clocks. Space contracts along the direction of motion, and simultaneity becomes relative. His insight unified mechanics, light, and gravity into one elegant picture governed by geometry rather than invisible forces. This framework has been tested for more than a century and never found wanting. From the bending of starlight to the precise timing of satellites, every experiment confirms it. Einstein's equations replaced old absolutes with relationships, showing that reality itself is dynamic, flexible, and guided by the shape of the space-time it inhabits.
Gravity is not a force, but the curvature of space-time. What we feel as gravity is not a pull exerted through space, but the natural motion of objects following curved paths within space-time. Massive bodies such as planets or stars distort the geometry around them, and other objects simply move along the straightest possible routes in that curved landscape. When you drop a ball, it is not being dragged downward. It is following the geometry that Earth's mass creates. The ground pushes up to stop it, creating the sensation of weight. Far above, satellites orbit by continually falling along paths that never quite reach the surface. Even light bends when passing near massive objects, following those same curves. This geometric explanation replaced the idea of gravity as a mysterious invisible tug, revealing instead a universe where motion and structure are one continuous, elegant system shaped by mass and energy. Mass tells space-time how to curve, and space-time tells mass how to move. This phrase, coined by physicist John Wheeler, perfectly summarizes general relativity. The presence of matter and energy determines the curvature of space-time, and that curvature dictates the motion of everything within it. The relationship is mutual and dynamic. When mass gathers, it bends the surrounding geometry, creating wells and ridges that define how particles and light travel. In turn, the motion and distribution of matter adjust those shapes continuously. This feedback loop governs orbits, tides, and the expansion of the cosmos itself. Einstein's field equations describe this interaction precisely, linking the contents of the universe to its geometry through a set of beautiful interlocking mathematical relationships. The result is a self-consistent cosmic architecture, one in which nothing moves arbitrarily. Every path, every fall, and every orbit arises naturally from the dialogue between matter and the structure of space-time itself. Space-time can be stretched, twisted, and warped. The geometry of space-time is not fixed or rigid. It can stretch as the universe expands, twist around rotating masses, and warp near dense regions such as stars or black holes. When galaxies drift apart, it is not because they are moving through space, but because the space between them is expanding. Near a spinning black hole, the twisting of space-time drags nearby matter and light into swirling patterns, a phenomenon called frame dragging. In laboratory and astronomical observations, light from distant stars shifts and bends as it passes through varying gravitational fields, revealing the invisible contours of space-time. These distortions are measurable, predictable, and fundamental to the behavior of the cosmos. The ability of space-time to deform gives rise to everything from gravitational lensing to the slow dance of planetary orbits, proving that the universe itself is built upon a living, flexible geometry. The presence of mass slows the flow of time. Time does not pass at a uniform rate everywhere. Near massive bodies, clocks tick more slowly compared to those farther away. This effect, known as gravitational time dilation, has been measured precisely using atomic clocks on Earth and in orbit. A clock on the surface of our planet runs slightly slower than one in a satellite, which must be corrected for GPS systems to remain accurate. The reason lies in space-time curvature. The deeper an object is within a gravitational well, the slower time progresses relative to distant observers. This is not an illusion, but a measurable physical reality. Around black holes, the difference becomes extreme. To a faraway observer, objects falling toward the event horizon appear to freeze in time, while for the falling object itself, everything proceeds normally. Gravity reshapes not only motion and space, but also the very rhythm of time itself. The faster you move, the slower time passes for you. Motion itself affects time. According to special relativity, the closer an object moves to the speed of light, the slower time passes for it relative to a stationary observer. This is called time dilation, and it has been verified through countless experiments with fast-moving particles and precise atomic clocks aboard high-speed aircraft. For example, muons created in the upper atmosphere live much longer when traveling near light speed than when at rest. Exactly as predicted, to the travelers themselves, nothing feels unusual. Time flows normally in their frame of reference. To outside observers, however, their clocks tick more slowly. If a spacecraft could reach near light velocities, its passengers might experience only a few years, while centuries pass back on Earth. This intertwining of motion and time means that no observer's experience of duration is universal. Every perspective is shaped by speed and relativity. Light always travels the same speed, no matter what. No matter how fast you move or which direction you travel, you will always measure the speed of light in a vacuum as exactly the same. This constancy is one of the foundations of modern physics and the reason relativity works at all. It means that space and time must adjust themselves by stretching, contracting, or dilating to keep light speed unchanged. Experiments have confirmed this endlessly, from Michelson and Morley's interferometer tests to modern laser and particle accelerator measurements. The result is that light's behavior sets an ultimate limit on information, energy, and motion. Nothing can outrun it. and everything that moves approaches it differently depending on its energy. This universal consistency is what allows the equations of physics to hold true everywhere, ensuring that the cosmos follows the same principles from the smallest atom to the farthest galaxy. The universe would not make sense without that constant speed of light. The unchanging speed of light anchors all physical laws because it remains fixed. Every observer in the universe can describe motion, energy, and time in a consistent way. It defines the conversion between mass and energy, dictates how information travels, and sets the structure of cause and effect. Without it, clocks and distances would lose meaning, and the fundamental equations that describe nature would collapse. The speed of light connects electromagnetism, relativity, and quantum theory into one coherent framework. It determines how fast signals can reach us from distant stars and how long we must wait to witness cosmic events. Even our definitions of the meter and the second depend on it. Light's constancy is the silent metronome of reality, a universal rhythm that unites the smallest particles with the farthest reaches of space-time. Your GPS would fail without relativity's time corrections. Modern navigation systems depend on satellites orbiting Earth, each equipped with atomic clocks that measure time with extraordinary precision. Yet these clocks do not tick at the same rate as those on the ground. The satellites move rapidly, which causes their clocks to run slower due to special relativity. At the same time, they are farther from Earth's gravitational pull, which makes their clocks run faster according to general relativity. The combined effect results in a daily timing drift of about 38 microseconds. Though tiny, this discrepancy would create location errors of several kilometers every day. If uncorrected, engineers account for these relativistic differences so that satellite time and ground time remain synchronized. Each time your phone calculates your position, it quietly uses Einstein's theories to adjust for these distortions, proving that even everyday technology must bow to the strange curvature of space-time. Time runs faster on a mountain than in a valley. Time itself flows at slightly different rates depending on where you are in Earth's gravitational field. A clock at the top of a mountain runs a little faster than one in a valley below. This difference, called gravitational time dilation, occurs because gravity slows the passage of time. The higher you go, the weaker the pull of gravity, and the faster time passes. The effect is incredibly small, but measurable with atomic clocks. In one experiment, scientists placed two synchronized clocks a few meters apart in height and detected a measurable difference in their ticking rates. Over a human lifetime, your head ages fractionally faster than your feet. Though minuscule, these differences matter in technology and science. They confirm that gravity and time are deeply connected, and that our experience of each passing second depends subtly on where we stand within Earth's curved space-time. The bending of light reveals the shape of space-time. When starlight passes near a massive object, its path curves. This bending is not caused by a force tugging at the light, but by the geometry of space-time itself. In 1919, astronomers observed this effect during a solar eclipse. They found that stars appeared slightly displaced from their usual positions as their light passed close to the sun. The measurements matched Einstein's predictions exactly and provided one of the first confirmations of general relativity. Today, scientists use this bending of light to study the invisible structure of the universe by observing how light from distant galaxies is deflected by clusters of matter. Astronomers can map regions filled with dark matter that emit no light at all. Every distorted image we see in deep space is a direct imprint of space-time's curvature, revealing that gravity shapes not just motion but the very path of light itself. Gravitational lensing turns space into a cosmic magnifying glass. When light from a distant galaxy passes near a massive object, such as a cluster of galaxies, the gravity of that cluster bends and focuses the light. The result is an effect known as gravitational lensing. Depending on the alignment, it can produce arcs, rings, or even multiple images of the same background object. This natural magnification allows astronomers to study galaxies that would otherwise be too faint or too far away to detect. It also reveals the distribution of dark matter, which makes up most of the mass in the lensing cluster. Scientists can analyze how the light is distorted to reconstruct a detailed map of the invisible structures shaping the cosmos. Gravitational lensing is one of the most powerful tools in modern astronomy, transforming space-time itself into a vast telescope that magnifies the universe's most hidden and distant realms. Black holes are regions where space-time collapses. When a massive star exhausts its nuclear fuel, gravity can crush its core to an extreme density, creating a black hole. In this state, the curvature of space-time becomes so intense that not even light can escape. The region's boundary, called the event horizon, marks the limit of visibility. Beyond it, gravity dominates so completely that space and time lose their usual meaning. At the center lies a singularity, a point where density and curvature become infinite and the now known laws of physics break down. To a distant observer, an object falling toward a black hole appears to slow and fade, never quite crossing the horizon. To the object itself, time flows normally as it plunges inward. Black holes are not holes in space, but regions where space-time itself has collapsed into a state of pure gravitational geometry. The edge of a black hole is called the event horizon. The event horizon surrounds every black hole and marks the point at which escape becomes impossible. It is not a solid surface, but a boundary in space-time, where gravity's pull equals the speed of light. Anything that crosses it, whether matter or radiation, is trapped forever. To an outside observer, objects falling toward the horizon appear to slow down, dim, and freeze in time. From the falling object's perspective, it passes smoothly through without noticing anything unusual. Quantum theory predicts that faint radiation escapes from just above this region, known as Hawking radiation, which causes black holes to slowly lose mass. The event horizon represents the meeting point of relativity and quantum mechanics, where our current understanding begins to fail. It is the cosmic boundary between what can be known and what will remain hidden inside the darkness forever. Inside a black hole, space and time switch roles. Within a black hole, the curvature of space-time becomes so extreme that the usual distinction between space and time breaks down. Crossing the event horizon changes the rules of motion completely. Once inside, moving forward in time means moving inevitably toward the singularity at the center. There is no path that leads away from it, because every possible direction points inward. To an outside observer, anything falling in appears to freeze at the edge, but to the falling object, the descent continues normally. This reversal shows that time and space are not fixed categories, but flexible aspects of geometry shaped by gravity. The singularity itself is not just a point in space, but a moment in time that everything inside must eventually reach. Inside a black hole, physics as we know it collapses into mystery. Space-time can ripple like a pond. Massive bodies such as black holes or neutron stars can disturb space-time so violently that ripples spread outward at the speed of light. These ripples are called gravitational waves. Einstein predicted their existence in 1916, but they remained undetected for nearly a century because their effects are so small. The passing gravitational wave changes the distance between objects by less than the width of a proton. In 2015, scientists finally detected them using instruments sensitive enough to measure these minute distortions. The signal came from two black holes colliding over 1 billion light-years away. Gravitational waves allow us to observe cosmic events that emit no light at all. They prove that space-time is not a static backdrop, but an elastic fabric that vibrates, carrying the stories of distant cataclysms across the universe like ripples on a vast cosmic ocean. Those ripples are what we call gravitational waves. Gravitational waves are distortions that travel through space-time whenever massive bodies move or collide. They are not sound or light, but ripples in the geometry of the universe itself. As they pass through Earth, they stretch and compress space by tiny amounts, detectable only with the most sensitive instruments. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made the first detection in The signal came from two black holes merging, confirming a century-old prediction. These waves have opened an entirely new field of astronomy that listens instead of looks. By studying their shapes and frequencies, scientists can determine the masses, distances, and spins of their sources, gravitational waves reveal events hidden from all telescopes, such as black hole collisions and neutron-star mergers, giving us a way to observe the universe through the motion of space-time itself. We have detected gravitational waves from colliding black holes. When two black holes orbit each other, they lose energy by sending out gravitational waves. As they draw closer, the waves grow stronger and more frequent, until the black holes finally merge in a burst of gravitational energy. In 2015, scientists detected the first of these signals after it traveled more than 1 billion light-years to reach Earth. The data revealed two black holes spiraling together before forming a single larger one. This event released more energy in a fraction of a second than all the stars in the observable universe combined. Each new detection since then provides unique information about the masses, spins, and distances of these cosmic giants. Listening to gravitational waves allows astronomers to study the universe through gravity itself, unlocking an entirely new way to explore events too dark to see directly. Every collision sends tremors through the fabric of the cosmos. When two massive bodies collide, space-time responds with ripples that radiate outward forever. These gravitational waves move at the speed of light, stretching and compressing space as they pass. Even now, faint echoes of ancient collisions are moving through you, changing the distance between atoms by less than a fraction of a proton. Instruments such as LIGO and Virgo can detect these minuscule tremors, allowing scientists to reconstruct the cosmic events that created them. Each signal is a fingerprint of a distant cataclysm, such as black holes merging or neutron stars smashing together. These observations confirm that the universe is dynamic and alive, filled with constant motion and energy. The cosmos is not silent, but filled with the quiet music of gravity, a rhythm of ripples spreading endlessly through the boundless ocean of space-time. Time dilation has been measured in airplanes. Einstein's prediction that moving clocks tick more slowly than stationary ones has been tested directly. In the 1970s, scientists placed atomic clocks aboard commercial airplanes and flew them around the world, while identical clocks remained on the ground. When compared, the flying clocks showed slight differences in elapsed time, precisely matching Einstein's equations. Both motion and altitude contributed to the effect. Higher speed caused time to slow, while weaker gravity at altitude made time run faster. The combined result matched the predictions perfectly. This experiment confirmed that relativity governs the passage of time, not only near black holes or stars, but also in everyday circumstances. Modern technology, from satellites to navigation systems, depends on these corrections. Every journey by air quietly demonstrates that time is flexible, flowing differently depending on speed and gravity's influence. Even your head ages faster than your feet. Gravitational time dilation affects you every second of your life. Because your head is slightly farther from Earth's center than your feet, it experiences a weaker gravitational pull, meaning time runs faster there. The difference is tiny, only a few billionths of a second over a lifetime, but it has been measured precisely using atomic clocks placed at different heights. In experiments, scientists have confirmed that even a height difference of a few centimeters changes how quickly time passes. This discovery demonstrates that gravity influences time everywhere, not just near massive stars or black holes. It also means that time is not uniform across the planet, or even within a single body. You live within a gentle gradient of time, where each heartbeat occurs in a slightly different moment than the one before, sculpted subtly by Earth's gravity. Space-time is four-dimensional, but we perceive only three. The universe contains 3 dimensions of space, which we know as length, width, and height, and a 4th dimension called time. Together, these form a unified structure known as space-time. We experience the spatial dimensions freely, moving in all directions, while time seems to flow in one. Physics, however, shows that space and time are part of the same continuum. Every event has both a location and a moment, inseparable from one another. Two observers moving differently through space will disagree about the passage of time, yet both will describe the same reality. Relativity unites the 4 dimensions under one consistent geometry, explaining motion, gravity, and causality. Although we cannot visualize 4 dimensions directly, mathematics reveals their harmony. The universe is not divided into space and time, but woven together into one seamless dynamic whole. The fourth dimension is time itself. When we speak of the fourth dimension, we are not describing an unseen direction in space, but time itself. Every event in the universe occurs at a specific place and a specific moment, requiring four coordinates to define completely. This view transforms our understanding of motion. Movement through space is also movement through time, because both are parts of the same framework. Observers in different states of motion will slice this four-dimensional reality differently, experiencing distinct versions of what they call now. Thinking of time as a dimension helps explain why simultaneity is relative and why cause and effect remain consistent, even when measurements vary. The fourth dimension is not mystical or abstract. It is an integral component of the geometry that binds the cosmos, connecting every point in space to every instant in history through the continuous structure of space-time. The universe may contain extra dimensions beyond the four we know. Some advanced theories in physics suggest that the familiar four dimensions might not be the entire picture. Ideas such as string theory and M-theory propose that additional dimensions exist hidden from our perception because they are compact and curled up at unimaginably small scales. These extra dimensions could explain why gravity is weaker than the other fundamental forces and how all the forces of nature might unify under one framework. Although we cannot observe these dimensions directly, their effects might appear in subtle gravitational measurements or high-energy particle collisions. Experiments continue to search for signs of these hidden layers of reality. If they are ever discovered, our understanding of the universe will expand dramatically, revealing that the space we move through every day may be only a small part of a much richer and more complex cosmic geometry. Tiny hidden dimensions could be curled up at subatomic scales. According to string theory, additional dimensions might exist everywhere around us, folded so tightly that they are smaller than atoms. These curled-up dimensions would determine the properties of particles, such as mass and charge, through the way they are shaped. Imagine a straw viewed from far away. It appears as a simple line, but up close, it has circular depth. Extra dimensions could behave similarly. Invisible at human scales, but vital to the universe's structure, they would exist at the Planck length, the smallest measurable scale, influencing how particles interact and how forces combine. Although these dimensions cannot be seen directly, physicists are searching for indirect evidence in particle accelerators and gravitational experiments. Discovering them would transform our understanding of reality, showing that space itself hides intricate patterns smaller and more fundamental than anything we have yet observed. String theory suggests there may be 10 or 11 dimensions. String theory proposes that the basic building blocks of reality are tiny vibrating strings rather than point-like particles. Each vibration corresponds to a specific particle or force. For the mathematics of this theory to be consistent, space-time must contain more than 4 dimensions, usually 10 or 11 depending on the version. The extra dimensions are thought to be compact and invisible at human scales, curled up so tightly that we cannot perceive them directly. These hidden dimensions allow the theory to unify all known forces, including gravity, into one coherent framework. Though experimental confirmation remains elusive, string theory has provided profound insights into black holes, quantum gravity, and the structure of the universe. It suggests that our visible world is only a small portion of a far greater dimensional reality waiting to be understood. If you could see all dimensions, reality would look entirely different. Our senses are limited to perceiving 3 dimensions of space, so we experience the world through surfaces, edges, and volumes. If we could perceive higher dimensions, everything would appear transformed. Objects that seem separate might be connected, and events that appear sequential might unfold together. In a higher dimensional perspective, distance and isolation could lose meaning. Mathematics allows us to imagine these realms, where geometry is richer and more complex than we can visualize. Some theories suggest that these dimensions influence the universe's fundamental properties, from particle behavior to cosmic structure. If we could see all dimensions, we might perceive entire timelines at once, and understand connections that now seem hidden. Higher dimensions challenge our understanding of existence itself, suggesting that the world we know may be only a narrow slice of a much deeper and more intricate reality. The Big Bang created both space and time together. The universe did not begin within space. Space itself began with the Big Bang. At that moment, the cosmos expanded from an incredibly hot and dense state, giving birth to both space and time simultaneously. There was no before this event, because time itself had not yet begun. As the universe expanded, matter and energy cooled and spread, eventually forming stars, galaxies, and planets. The faint afterglow of this event, the cosmic microwave background, still fills the sky today. Modern cosmology shows that space-time is not a static container, but a dynamic entity that evolves with the universe. Asking what happened before the Big Bang is like asking what lies north of the North Pole. The concept simply does not apply. The beginning of space-time marks the origin of everything, the first moment from which all moments flow. There was no before the Big Bang. The Big Bang was not an explosion inside space. It was the creation of space and time themselves. Before it happened, before had no meaning. The laws of physics break down when traced back to that singular point. Again, asking what came before the Big Bang is like asking what lies north of the North Pole. The question loses meaning. Time began as the universe expanded from infinite density and temperature into the vast cosmos we see now. Every second, every atom, every star came from that first unfolding. In those earliest instants, space and time were intertwined, forming the foundation upon which all cosmic structure would later rise. The universe has no center. Expansion happens everywhere. When we look out, galaxies appear to move away from us in every direction. It creates the illusion that Earth is at the center, but that is not the case. The expansion of the universe is not an explosion into empty space. It is the stretching of space itself. Every point in the cosmos sees the same pattern. Galaxies are not moving through space. Space is expanding. The galaxies themselves remain relatively stable, held by gravity, while the fabric of space-time stretches around them. Light traveling through expanding space gets stretched too, leading to the redshift astronomers observe. This redshift is direct evidence that the universe is expanding. To visualize this, imagine dots on the surface of a balloon. As the balloon inflates, the dots move apart, not because they travel, but because the surface expands. Similarly, space stretches, increasing distance between galaxies without motion through an external void. There is no edge, no center. Expansion simply happens everywhere. The expansion of the universe is accelerating. Scientists once thought gravity would slow expansion, but distant supernovae revealed otherwise. The universe is not slowing. It is speeding up. Something is pushing galaxies apart with increasing strength. That something is dark energy, the invisible driver of cosmic acceleration. It fills all of space evenly. It repels rather than attracts. It makes up about 70% of the universe. We do not know what it is. It does not emit light, does not interact with matter, does not form structures. It just pushes space itself to expand faster. The geometry of the universe depends on its density. High density gives a closed universe. Low density gives an open universe. Perfect balance gives a flat universe. Evidence suggests the universe is almost perfectly flat, a balance likely set by cosmic inflation. If curved enough, the universe could loop back on itself. If dense, it may end in a big crunch. If open, it will expand forever into cold emptiness. Geometry becomes destiny. Even empty space is not empty. Quantum fields, virtual particles, and fluctuations fill every region of vacuum. Space is alive. The vacuum is not nothing. It is the foundation of reality. Quantum fluctuations may have seeded the first galaxies. And then there is the Planck scale, the frontier of reality. Time itself may be quantized. Space-time becomes foamy at the Planck scale. Below the Planck length, space loses meaning. Below the Planck time, time loses meaning. Here, quantum mechanics and gravity must merge, forming quantum gravity. Spacetime might not even be fundamental. It may be emergent, born from deeper information or entanglement. The cosmos may therefore be a vast web of entanglement, each thread holding together the structure of everything that exists. Some theories suggest space is built from quantum information. Modern physics increasingly points to information as the true foundation of reality. In some theories, every point in space corresponds to a tiny unit of data describing the quantum state of the universe. These formational bits interact, exchange energy, and together create what we perceive as geometry and motion. Evidence for this comes from black holes, which appear to store their contents not in volume but on their surface area. The amount of information they contain scales with that area, implying that space itself might be quantized in similar ways. If the universe is made of information, then physics is a process of computation, and every particle interaction is a kind of calculation. Space would be the structure of that ongoing computation, a holographic lattice of relationships that encodes everything we see, feel, and measure within the vast machinery of the cosmos. Time may flow from the growth of entanglement. Time might not be an independent background in which events unfold, but an emergent property of increasing quantum connection. As systems interact, they become more entangled, forming a web of relationships that grows more complex over time. This rise in entanglement could define the direction of time itself. The universe evolves from simpler states to more correlated ones, giving rise to the arrow of time that points from past to future. In this sense, time is not a fundamental dimension, but a reflection of change in the informational structure of the cosmos. As particles exchange information, the fabric of space-time evolves with them. Clocks measure not a pre-existing flow, but the rate at which systems build correlations. Time becomes the story told by the universe, as it knits together its own structure through entanglement, weaving history from pure quantum connection. The arrow of time points from order to disorder. The flow of time has a clear direction that we experience every moment. Yet the laws of physics themselves do not prefer one direction over another. The reason we perceive time as moving forward is because of entropy, the measure of disorder. Entropy always increases in closed systems, meaning the universe evolves from more ordered states to less ordered ones. Broken glass does not reassemble, and heat does not flow from cold to hot without work. The early universe was remarkably ordered, allowing time to have a distinct direction as entropy rose. This gradual increase gives rise to memory, causality, and change. Without it, all events would seem reversible, and the difference between past and future would vanish. Entropy is not merely a statistical property, but the cosmic engine that gives time its one-way current, turning symmetry into history and stillness into motion. Entropy gives time its direction. Entropy describes how many possible arrangements a system can take while maintaining the same overall appearance. As entropy increases, more configurations become possible, and systems drift naturally toward disorder. This process explains why time seems to move forward. To reverse it would require every particle to retrace its path exactly, an event so improbable that it would never occur in practice. The increase of entropy underlies everything from melting ice to the evolution of galaxies. The universe began in a state of exceptionally low entropy, and its steady rise has created the sense of flow and progression we call time. Each irreversible process we observe, from the burning of stars to the beating of a human heart, is a manifestation of this deep rule. Time's arrow is drawn by the mathematics of probability written across every movement of matter and energy. If entropy decreased, time might run backward. If entropy were ever to decrease universally, the distinction between past and future would vanish. Events would unfold in reverse order, with chaos giving way to order, and broken systems spontaneously repairing themselves. Physics allows this in principle, but not in practice, because it is so statistically unlikely. The number of ways for particles to arrange into disorder far exceeds the number that creates structure. A universe with decreasing entropy would erase memory and causality, because causes would follow effects instead of preceding them. Such a reversal challenges our deepest intuitions about time and existence. Although entropy can locally decrease, as in the growth of life or the formation of stars, These processes always produce greater disorder elsewhere. Time's forward motion is therefore sustained by the overall rise of entropy, anchoring every moment in the irreversible unfolding of cosmic history. The early universe was more ordered than today. Immediately after the Big Bang, the universe was smooth, uniform, and dense. Despite its apparent chaos, this was a state of extremely low entropy, meaning it was far more ordered than today's structured cosmos. There were few possible configurations for matter and energy to occupy. Over billions of years, as the universe expanded and cooled, tiny fluctuations grew into stars, galaxies, and planets, greatly increasing entropy. This rise defines the arrow of time. The early simplicity allowed complex structures to emerge as entropy grew, leading to life, evolution, and change. Scientists still do not fully understand why the universe began in such an improbably ordered state. The answer could reveal why time has direction at all. The universe's evolution from smoothness to complexity is not decay but transformation, a continuous balancing act between order and chaos that drives cosmic history. Every second that passes increases the universe's entropy. Entropy grows steadily throughout the universe, shaping the arrow of time. Every process that converts energy from one form to another contributes to this increase. Stars fuse hydrogen into helium, radiating heat into the cosmos. Black holes consume matter and light, adding to their immense entropy. Living organisms metabolize energy, creating local order, while releasing waste heat. Each of these actions marks a small step in the universal rise of disorder. Over billions of years, entropy has increased so much that most of the cosmos is now cold and diffuse, with energy spread thinly across vast distances. Yet, this ongoing process also fuels creativity and complexity. The flow of energy from order to disorder allows systems like planets and life to exist briefly in between. Every second that passes deepens entropy's imprint, recording the irreversible rhythm of the universe's unfolding story. Time moves differently near massive objects. Gravity warps not only space, but also the flow of time. Near a massive body, clocks tick more slowly than in regions where gravity is weak. This phenomenon, called gravitational time dilation, has been confirmed by experiments comparing atomic clocks on Earth and in orbit. The closer a clock is to a planet or star, the more the curvature of space-time stretches time itself. Near a black hole, this effect becomes extreme, with seconds turning into centuries relative to distant observers. The principle is woven into technologies like GPS, which must account for these relativistic differences to function accurately. Time dilation reveals that the universe's rhythm is not absolute but elastic, shaped by gravity's invisible pull. Mass and time are inseparable partners, each influencing the other, creating a cosmos where every heartbeat, every orbit, and every light beam unfolds within curved geometry. Around a black hole, seconds can stretch into eternity. As matter approaches the event horizon of a black hole, the curvature of space-time becomes so intense that time nearly stops from the perspective of a distant observer. To that observer, the falling object appears to freeze in place, fading slowly as its light redshifts into invisibility. Yet, for the object itself, time proceeds normally. It crosses the horizon in a finite interval, unaware of how distorted the outside world has become. This paradox illustrates the relativity of time and the power of gravity to bend it. The region near a black hole's horizon is an arena where the geometry of space-time dominates every process, turning seconds into eternities and motion into stillness. What seems eternal from afar is, in another frame, a momentary fall. The boundary between these perspectives defines one of the most beautiful mysteries in all of physics. Near a black hole's edge, light itself struggles to escape. The edge of a black hole, known as the event horizon, marks the ultimate gravitational threshold. At this distance, the pull of gravity exactly equals the speed of light's outward motion. Any closer, and even photons cannot climb away. As light tries to escape from near this region, it loses energy, stretching into longer wavelengths that eventually fade into darkness. This effect, called gravitational redshift, shows that light itself obeys the curvature of space-time. Observing how radiation bends and slows near black holes allows astronomers to test the predictions of general relativity with extraordinary precision. The struggle of light to emerge from such depths reveals that space and gravity are inseparable. Black holes do not trap light by force alone, but by geometry itself, reshaping the very fabric of the universe so that all paths curve back toward the unseen center. To a distant observer, an object falling in seems to freeze in time. When an object falls toward a black hole, it appears to slow and fade as it nears the event horizon. From far away, the process seems to take forever. As time dilation stretches each moment infinitely, the object's light grows redder and dimmer until it vanishes completely. To the falling object, however, everything feels normal. It crosses the horizon and continues inward without noticing anything special. This difference arises because time and space behave differently for observers in distinct gravitational fields. The black hole's immense curvature causes their perspectives to diverge completely. The frozen image seen from afar is not a trick of vision, but a real manifestation of space-time geometry. It demonstrates that time is relative, shaped by gravity, motion, and position. Near a black hole, even the flow of moments becomes a matter of perspective and distance. To the object itself, it crosses the horizon without noticing. From the viewpoint of an object falling into a black hole, the event horizon is not a wall or barrier, but an ordinary region of space-time. The traveler feels no sudden force or change while crossing it. Locally, physics continues as usual. Yet, from an external perspective, the same event looks frozen forever, just above the horizon. This paradox illustrates how gravity warps not only space and time, but perception itself. Inside the horizon, all possible paths lead inward toward the singularity, a point where known physics breaks down. For the falling object, the crossing is inevitable and unremarkable. But for an outside observer, it never truly happens. The two perspectives are equally valid within their own frames. This profound contrast reveals that reality in general, relativity depends on where you stand and how deeply gravity shapes the passage of your time. Space and time are perceived differently by every observer. Einstein's theory of relativity teaches that space and time are not absolute. Two observers moving at different speeds or located in different gravitational fields will measure different intervals of time and distance between the same events. What one calls simultaneous, another may see as sequential. This relativity of perception arises because space-time itself adjusts to preserve the constant speed of light. Clocks slow down, and length contract to maintain this universal balance. Everyday life hides these effects, but at high speeds or strong gravity they become profound. This principle reshapes how we understand motion, cause, and even existence. There is no single shared timeline threading through the universe and the countless personal timelines that intersect and diverge. Reality then is not fixed from a single viewpoint, but stitched together from the overlapping perspectives of all who move through the geometry of space-time. Simultaneity is an illusion. Events that seem to happen at the same moment for one observer may occur at different times for another who is moving relative to them. This effect, known as the relativity of simultaneity, follows directly from the constancy of the speed of light. Since light always travels at the same speed, observers moving differently must adjust their measurements of time and space to remain consistent. This means there is no universal now shared across the cosmos. Every observer carries their own slice of reality defined by motion and position. What appears synchronized in one frame can unfold sequentially in another. This idea challenges the intuition that time is absolute, but has been proven repeatedly through experiment and observation. The universe does not tick in unison, but hums in countless overlapping rhythms, each tied to its observer's unique motion through space-time. Relativity teaches us that space and time are not rigid backdrops, but living parts of the universe's geometry, stretching, bending, and reshaping themselves to preserve the harmony of physical laws. Every effect we observe, from time dilation to length contraction, from light cones to causality, reveals a cosmos guided not by chaos but by exquisite order. Even the most exotic possibilities, wormholes, negative energy, and closed time-like curves, emerge naturally from the same elegant equations that describe falling apples and orbiting planets. Though we have never seen these extreme structures, their mathematical existence shows us that reality is far deeper than our everyday intuitions. Relativity dissolves the boundaries between past, present, and future, but it also protects the universe from paradox and contradiction. Whether through the strict geometry of light cones or the whispered safeguard of Hawking's chronology protection, space-time maintains consistency at every scale. In the end, the universe is not simply a stage on which events unfold, it is an active participant shaping motion, guiding light, and defining the limits of what can be known, reached, or changed. Relativity does not just describe the universe, it reveals the profound unity woven into its fabric, a cosmos where space and time dance together, where geometry governs reality, and where every observer, no matter how they move, witnesses the same underlying truth. This example captures the essence of relativity, which abolishes the idea of a single universal time. The concept of simultaneity depends on an observer's state of motion, proving that time is woven into space and cannot be separated from it. This relativity of experience does not create contradiction, but harmony. It ensures that all observers agree on physical laws, even if they disagree on when events occur. Time and space adapt perfectly to preserve the unity of the universe's geometry. Moving clocks tick differently than stationary ones. Einstein discovered that time does not flow at a fixed rate for everyone. When an object moves at high speed, its internal clock slows relative to one that remains at rest. This strange effect, known as time dilation, has been confirmed in many ways. Subatomic particles that should decay in a fraction of a second survive much longer when traveling close to light speed. Atomic clocks aboard airplanes or satellites run slightly slower than identical clocks on Earth's surface. None of this is illusion. It is how the universe maintains the consistency of physical laws. Every observer, moving or still, measures the same speed of light, and to make that possible, time itself must adjust. The faster an object moves, the slower its seconds pass. This quiet stretching of time keeps the entire cosmos harmonious, linking motion, light, and experience in a single elegant geometry. Moving rulers shrink in the direction of motion. Just as time slows for moving objects, space also adjusts. A ruler or spacecraft traveling at high speed will appear shorter along the direction of its motion when measured by someone at rest. This effect, known as length contraction, is a natural partner to time dilation. Both arise because the speed of light is constant for all observers, no matter how they move. To preserve that constancy, space and time must shift together. The object itself experiences no change within its own frame. Everything feels normal, but to an outside observer, distances compress and time stretch, ensuring that the laws of physics never contradict one another. Experiments using high-energy particles have confirmed this repeatedly. As they race through accelerators, their paths and lifetimes behave exactly as relativity predicts. Space and time bend together in perfect coordination, maintaining the balance that underlies the entire universe. Space contracts just as time dilates. Relativity unites space and time into a single structure, and they flex together whenever motion occurs. As an object speeds up, its measure of time slows while its length shortens along its direction of travel. These effects preserve the constancy of light speed and ensure that physical laws remain identical for all observers. The interplay of stretching time and contracting space reveals that neither quantity exists independently. They are coordinates in a deeper geometry that defines reality itself. For astronauts traveling near the speed of light, the universe ahead would seem compressed, while those remaining on Earth would see the travelers' clocks ticking more slowly. Each observer experiences a consistent world, yet their measurements differ in ways that precisely mirror one another. The balance between space and time is what keeps the universe coherent, turning relativity from paradox into perfect harmony. Together, they keep the speed of light constant. No experiment has ever found light to travel at any speed other than its universal value in a vacuum. Whether the source moves toward you or away, whether you are running beside it or standing still, the result is always identical. This constancy might seem impossible unless space and time themselves adjust to preserve it. That is exactly what relativity describes. Moving clocks slow, moving distances shorten, and both effects cooperate to ensure that the measured speed of light remains fixed. This consistency allows the equations of nature to hold true for everyone regardless of motion. It also establishes light as the ultimate messenger of the universe, defining the limits of communication and causality. Every photon travels within a structure that reshapes itself to maintain equilibrium, reminding us that even the simplest constant hides profound unity between distance, duration, and the geometry of reality. Space-time diagrams help visualize this interdependence. To understand how space and time combine, physicists use space-time diagrams. These diagrams plot position on one axis and time on another, turning abstract equations into geometry. Every object follows a world line, a path that shows where and when it exists. A stationary object traces a vertical line upward through time, while a fast-moving one tilts toward the horizontal, revealing how motion blends space and time together. The slope of light's world line defines the speed limit for all motion. Within this picture, time dilation and length contraction appear naturally as simple geometric relationships. The diagram also helps visualize cause and effect, showing which events can influence others and which remain forever disconnected. Space-time diagrams transform relativity into something we can picture, showing that every life, every signal, and every journey is a thread woven through the same four-dimensional tapestry that defines the universe. Light cones show which events can influence each other. In the fabric of space-time, every event sends out potential paths for light. In all directions, these paths form what physicists call a light cone, the region of space and time that can be reached or affected by that event. The inside of the cone represents everything that can be touched by its influence, while the outside marks what will forever remain unreachable. Light cones define causality, determining which events can affect which others. They grow wider as time progresses, expanding the region of possible influence, but they always remain bounded by the unbreakable limit set by light speed. The geometry of these cones shows why cause must precede effect, and why faster-than-light travel would disrupt reality itself. Every action, from a spark to a supernova, lives within its own cone, shaping the web of connections that give structure and order to the cosmos. Inside your light cone lies everything that can affect you. From the moment of your birth, every photon, sound wave, or particle that has ever touched you has traveled within your light cone. This invisible region defines your personal portion of the universe, containing all events that could possibly influence you and all future events you could someday reach. Everything outside it lies forever beyond your causal contact. The shape of this cone expands with each passing moment, but its boundaries are strict, limited by light's constant speed. Even if you journeyed across galaxies, you could never reach certain distant points in space or times in the future that fall beyond its reach. Your entire life unfolds inside this geometric enclosure. It connects you to everything you have ever seen or felt, while reminding you that most of the universe lies forever beyond the frontier of your possible experience. Outside it lies everything forever beyond reach. The vast majority of the cosmos will remain forever outside your light cone. No matter how long you wait or how far you travel, its signals can never reach you. This limitation arises not from technology, but from the fundamental nature of space-time itself. Light's finite speed defines the maximum extent of influence. Galaxies far enough away recede faster than light due to cosmic expansion, placing them permanently beyond communication. Their light will never arrive, their stories forever unreadable. The geometry of space-time draws an absolute horizon around every observer, defining a private universe bounded by time and distance. It is a sobering thought that isolation is built into the structure of reality, yet it also gives meaning to connection. Within that reachable region, every ray of light and every shared moment carries immeasurable value, bridging the finite with the infinite through pure geometry. Causality depends on the geometry of space-time. The rule that cause must precede effect is not merely philosophical, but a consequence of geometry. The structure of space-time, with its like cones and curvature, enforces a natural order of events. Nothing can travel outside its cone without violating the universal speed limit, so no cause can influence something before it occurs. When space-time curves around massive objects, these cones tilt and distort, changing the flow of time and the pathways of light. Yet, even in the warped regions near black holes, the principle remains intact. This geometric enforcement ensures that reality remains coherent and predictable. Without it, events could occur in inconsistent orders, and the universe would lose its logical structure. Causality is the quiet architecture beneath every experience, sculpted not by human reasoning but by the fundamental shape of space-time itself, which preserve consistency throughout the cosmic fabric. Wormholes could bend that geometry in astonishing ways. The equations of general relativity permit solutions in which space-time folds in on itself, creating tunnels that connect to distant regions. These theoretical structures are called wormholes. In essence, a wormhole is a shortcut through the fabric of the universe, allowing a traveler to move between two far-separated points without crossing the space in between. While they have not been observed, their mathematics is sound, suggesting they could exist under the right conditions. Some wormholes would collapse instantly, while others might remain stable if held open by negative energy, a form of matter with unusual gravitational properties. If such structures exist, they could revolutionize our understanding of distance and connection. They show that space-time is not merely a stage, but a living, flexible entity capable of astonishing configurations that challenge our deepest intuitions about separation and motion across the cosmos. A wormhole links two distant regions of space-time. Imagine taking a sheet of paper, drawing two dots far apart, and folding it so the dots touch. A wormhole is the space-time equivalent of that fold, linking distant points in a single continuous structure. In theory, one could enter a wormhole near Earth and emerge near another star, or even another galaxy, almost instantly. Mathematically, general relativity allows such connections, though keeping them open would require exotic matter with properties not yet observed. Wormholes might exist at microscopic scales, forming and vanishing in the quantum foam of the universe. Others, if large enough, could serve as cosmic bridges. While purely hypothetical for now, their study expands our understanding of relativity, geometry, and energy. Wormholes reveal that space is not rigid, but pliable, capable of configurations that merge distant regions into one seamless continuum of cosmic possibility. They are allowed by Einstein's equations in theory. When Einstein's field equations are explored deeply, they reveal solutions that describe wormholes, time loops, and curved pathways connecting remote parts of space-time. These are not science fiction inventions, but legitimate mathematical results that arise naturally from general relativity. Whether nature actually constructs them is an open question. The conditions required may be extreme, involving gravitational fields so intense and energy densities so exotic that they stretch our current understanding of physics. Yet their mere possibility demonstrates the flexibility of space-time and the depth of Einstein's insight. By translating gravity into geometry, his equations permit universes far stranger than the one we observe. Wormholes, if they exist, would not break the rules of physics, but would instead express them fully, showing that the cosmos is capable of shapes and pathways beyond the limits of ordinary perception. A traversable wormhole might require exotic matter. A wormhole stable enough to pass through would collapse instantly under its own gravity unless something held it open. Theoretical models suggest that this support could come from exotic matter, a substance with negative energy density. Such material would behave in ways completely opposite to ordinary matter, repelling rather than attracting through gravity. Negative energy does appear in certain quantum phenomena, such as the Casimir effect, but only in minute quantities. To hold a wormhole open, one would need enough of it to counteract immense gravitational pressure. Although the idea remains speculative, it demonstrates how relativity and quantum mechanics intersect. The study of exotic matter pushes physicists toward a unified understanding of both realms. If traversable wormholes ever prove real, they will reveal not only new routes through space, but profound connections between gravity, quantum fields, and the deep structure of space-time. Negative energy could hold a wormhole open. Ordinary matter cannot prevent a wormhole from collapsing, but negative energy might. In quantum theory, negative energy occurs in certain situations where the vacuum behaves unusually, such as between two closely spaced metal plates in the Casimir effect. This type of energy exerts a repulsive gravitational influence, the opposite of what we experience in daily life. If enough could be produced and controlled, it might keep the throat of the wormhole stable, allowing safe passage. Although no experiment has achieved this, the concept links quantum mechanics and general relativity in remarkable ways. It shows that the smallest scales of reality could influence the largest, with quantum fluctuations determining the fate of cosmic structures, whether or not such a feat is ever realized. The idea of negative energy reminds us that space-time remains full of undiscovered possibilities and strange hidden forces. We have never observed one yet. Despite decades of searching, astronomers have found no direct evidence of wormholes, no unusual gravitational signatures, light distortions, or repeating signals indicate that such tunnels exist. That absence, however, does not disprove them. Wormholes, if real, could be rare, unstable, or hidden behind horizons. Detecting one would require immense precision and perhaps new technology capable of identifying their subtle effects on nearby light and matter. Even without proof, scientists study them because they stretch the boundaries of known physics, offering insights into gravity, geometry, and energy. They also serve as valuable thought experiments that help test the limits of Einstein's equations. The mystery endures, fueling imagination and research alike. Whether wormholes remain theoretical or someday become observable, their existence in mathematics shows how deeply the structure of space-time can surprise us with its beauty and complexity. Time travel might be possible through certain wormholes. Some solutions to Einstein's equations suggest that wormholes could connect not just distant points in space, but different moments in time. If one mouth of a wormhole experienced time more slowly than the other, perhaps through motion or gravity, traveling through it might allow a return to the past or a leap into the future. Such possibilities raise profound questions about causality and paradox. Could you visit your earlier self or change an event that has already happened? Most physicists believe nature would prevent such violations, but the mathematics itself does not forbid them completely. Exploring these ideas helps scientists probe the limits of general relativity and the nature of time itself. Whether practical or not, wormholes remain a theoretical bridge between the familiar flow of time and the deeper, more flexible geometry that underlies the universe. But paradoxes make it complicated. The notion of time travel immediately confronts the problem of contradiction. If you could journey to the past, could you prevent your own existence? Such logical puzzles, known as paradoxes, challenge the consistency of causality. Physicists have proposed many resolutions. Some suggest that the universe forbids paradoxes through a principle of self-consistency, ensuring that any trip to the past simply fulfills history rather than changing it. Others argue that time travel might lead to branching timelines or parallel realities. However, without experimental evidence, these remain ideas rather than realities. The mathematics of general relativity permits closed time-like curves, pathways that loop through time, but quantum mechanics may prevent them from forming. In this tension lies one of physics's greatest mysteries. Whether time's flow is absolute, or whether the universe, through its geometry, can bend that flow into strange and self-consistent shapes. Closed time-like curves could allow loops in time. In certain solutions to Einstein's equations, spacetime can curl back upon itself, creating what physicists call closed time-like curves. These are paths that return to their own starting points in time, allowing an object to revisit its past. Such configurations arise in theoretical models involving rotating universes or wormholes, though none have been observed in nature. If they existed, they would challenge our understanding of causality and the sequence of events, yet the equations themselves do not forbid them, showing that relativity allows more flexibility than intuition suggests. Many scientists believe quantum effects or cosmic censorship prevent such loops from forming, preserving order in the universe. Still, the idea fascinates researchers because it reveals how time, under extreme conditions, could behave like a spatial dimension, folding and connecting in ways that blur the boundary between past and future. The universe may protect itself from paradoxes through chronology protection. Stephen Hawking proposed that the laws of physics contain a safeguard called chronology protection, preventing time loops that would lead to paradoxes. In this view, any attempt to create a closed time-like curve would trigger quantum effects that destroy the configuration before it could form. Energy levels might rise to infinity, tearing the space-time apart or sealing the wormhole that would permit backward travel.